and the other one, which is what we're working with at NASA. So we have teams at both places. The NASA side of it is called Restore L, which is a low Earth orbit satellite. In fact, it's Landsat 7, and we're going to grapple with Labsat 7 and then refuel it in orbit. That's never been done before. The robotics and all of the components and everything that go along with it have never been used before. We're inventing all of this stuff as we go. And of course, we're getting some great support from the NASA roboticists. And we have our own roboticists. So we have most of our guys on that work for PTR. I mean, we're a small company. We're about 35 folks. But our typical engineer has 18 to 20 years worth of experience. So, we've been doing embedded systems controls, flight software, and all that sort of business for quite some time. The company itself was actually, this is our 18th year. We were founded in 2000. So, as a corporation, we've been around for a while. And then, we've just managed to get into some of these programs like Restore L and RSGS, the DARPA program, and it's just really cutting edge stuff. So, as a matter of fact, I had an opportunity to go by and visit my group over at NASA when I was over there teaching a class last week. And it was fantastic to actually see all of the equipment and see what they're trying to do, some real physics problem kind of things. It's like when you're trying to grab a hold of a 2-ton satellite in orbit as it's moving at orbital velocities. Even the slightest mistake ends up in a debris cloud that violates all kinds of treaties.
So we're all trying to focus on the science, and we have to worry about that as well.
Well, yes, and that's really, I mean, the science part of it is difficult, and it's a really complicated problem. Lots of embedded control theory, lots of, I mean, the folks at NASA, the folks that we've been working with. I mean, we're inventing tools to make this thing work. The little gripper, as a matter of fact, the arm that comes off of the satellite has to be able to change tools because we need to be able to cut wires. We need to be able to grab a hold of a filler cap and unscrew it. We need to be able to pull mylar back off of the heat shields. We need to put in new fuel. And then we have to undo all of that. And that all has to be done while the satellite is orbiting. The bigger problem here is that the satellite is too far away for humans to control it. So most of this stuff has to be done autonomously. So the satellite basically runs itself. Once we get it close to the actual Landsat 7, the bird itself, it takes over and runs itself. So it's really pretty remarkable stuff, even from an artificial intelligence perspective.
Are you running, how are you testing this? Are you running virtual models that run this over and over and over to simulate it?
We do have some simulation, but we actually have mock-ups of all of this equipment. It's in a big bay there at NASA Goddard Space Flight Center, and we're actually testing it on life-sized devices with life-size robots. So some of the robots we have are like 6 degree of freedom, 7 degree of freedom, 2-ton robots, industrial robots that have been modified specifically for this particular application. So we're running through all of the software control stuff here on the ground. We've already done some testing on the Vomit Comet. That is the aircraft that goes up and down to test microgravity.
Mm-hmm.
So we've already done some testing on that with some scale models. So we're actually approaching it from several different perspectives, both a simulation perspective, a scale model perspective, and a life-sized model perspective with all the weights and everything. We've even been able to instrument the robotic arm so that it behaves like it's in space. So if you walked up to it and touched it with your finger, it would actually start to move.
Whoa.
Yeah, so
Is it a lot of, is it very difficult dealing with, like, so you have these, you mentioned two physical things that are in the real world that are models, and then you go into a space that doesn't have gravity. How do you compensate for the difference in running, like knowing your physical models working when you don't have the same?
well, fortunately, NASA has quite a bit of history in terms of understanding how large devices operate in space. We can certainly take some of the history that we've gotten from the Hubble Space Telescope. Of course, all the work that they've done on the International Space Station. So we have a fairly good history in terms of being able to understand how the physics are supposed to work. And we actually do have an arm that's on the International Space Station that we've used for testing some of this stuff. So we are actually doing some live testing on real robotic arms in zero G on the space station itself. So